Hello, and welcome to my video series of algorithms. This is part 3 of Module 5, Divide and Conquer Algorithms. In this video, we will discuss the closest pair of points problem. Imagine that you are an epidemiologist aiming to identify the source of an outbreak. The only information at your disposal is a map marked with the locations of the identified cases. Without additional information, such as the evolution pattern of the pathogen, we can only assume that the closer the locations, the more likely the pathogen can spread between them. In this case, the highest likelihood of pathogen infection occurs between the two sites that are the closest among all pair of sites. Therefore, you can infer that location near the closest pair of sites are the likely source of the outbreak. This example motivates the following computational problem. Given a set of endpoints, each represented by a two-dimensional coordinate xi, yi, find the closest pair of points. You can think of the coordinates xi, yi as the latitude and longitude in the map. This problem is known as the two-dimensional closest pair of points problem. The naive solution to the problem is to compute the distance between all pairs of points. This strategy would take O(n) squared time complexity, where n is the number of points in the 2D space. In reality, we could have millions of reported cases. In this scenario, an O(n) squared time complexity is obviously too slow to be feasible. Therefore, we need to develop a faster algorithm. So, how fast should it be? Interestingly, the one-dimensional closest pair of points problem has a simple solution that runs in O(n) log n time. To solve it, we simply sort the points by their coordinates and scan the sorted points to identify the closest pair. Unfortunately, this simple sorting strategy cannot be directly applied to the 2D case. This is because points that are close in one dimension are not necessarily close in the entire space. For example, the x-axis distance between the two green points is 0. Similarly, the y-axis distance between the two pink points is 0. However, the closest pair of points is neither of those pairs, but the one highlighted by the oval. Despite this, the algorithm for the 1D closest pair of points problem suggests that we could develop an algorithm that runs in O(n) log n time for the 2D case. Given that we have devised several O(n) log n algorithms using divide and conquer, we aim to do the same here. Let's begin with the divide step. We can simply divide the set of points into two equal-sized subsets. Say we draw a vertical divider line to split the entire space into two subspaces, Q and R. Note that the entire space is finite and can be defined by the minimum and maximum coordinates of the points. Therefore, the subspaces Q and R are also finite. Also, note that Q and R do not necessarily have the same area, but that they should contain the same number of points. The divider line is described as a function x equals to x0, where x0 is the median x-coordinates among all points. Now, let's discuss the merge step. Clearly, the closest pair of points in the whole space is the minimum among the following three minimums: the closest pair where both points are in Q, the closest pair where both points are in R, and the closest pair where one point is in Q and the other is in R. In other words, the closest pair of points of the entire space is the minimum among the two closest within space pairs and the one between space pair. Using recursion, we can obtain the two within space pairs. The challenge is to find the closest between space pair. To determine whether using divide and conquer can improve speed, we need to analyze whether it uses fewer computations compared to the direct solution. The naive solution that directly considers all combinations of 2 points needs to compute n squared over 2 distances. Using divide and conquer, Each subspace now contains n over 2 points. In this case, solving each subproblem requires the computation of n squared over 8 distances, which is obtained by replacing n in the previous formula with n over 2. In other words, we need to spend n squared over 8 computations to find the within space closest pair of points in Q, and the same amount of computation to find that in R. To compute the between space closest pair of points, we can use a brute force approach to enumerate all between space point combinations. Since Q contains n over 2 points, and R also contains n over 2 points, we need to compute n squared over 4 distances. Summing them together, we obtain that the total amount of computation needed is n squared over 2, the same as the naive solution. As a result, this simple divide and conquer approach does not save us computation, and we need to do better. From our prior experience with the merge sort algorithm, we know that if the divide step splits the input into 2 equal size subsets, the merge step needs to run in linear time to achieve an O n log n time complexity. However, if we enumerate all between space pairs, we need to compute n squared over 4 distances, which corresponds to an O n squared time complexity. Therefore, we should eliminate unnecessary computations by reducing the number of between space pairs considered. Before delving into the details, let's first define some notations. Denote the minimum within space distance in subspace Q as delta Q, and that for subspace R as delta R. Also, denote the smaller between delta Q and delta R as delta min. Finally, let the minimum between space distance in the entire space be delta QR. Now, let's make a very important observation. Recall that the minimum distance in the entire space should be the smaller one between the shortest within space distance and the shortest between space distance. Given the shortest within space distance, delta min, a larger between space distance will not contribute to the final solution. In other words, we can safely discard between space pairs if we know that their distances are surely larger than delta min. With this intuition, we can define a vertical band with the radius of delta min around the divider line, shown in the figure as the yellow band. You can easily verify that for any between space pair of points where at least one point is outside the band, their distance must be larger than delta min. As a result, we shall only focus on computing the distances of the between space points that are both within the band. In the example shown in the figure, there are only 4 points in the band, with 2 in Q and 2 in R. In this case, we only need to compute 4 between space distances. While this method reduces the number of distances to compute, does it lead to an improvement in time complexity? Unfortunately, in the worst-case scenario, we could have all points clustered within the band, as shown in the right figure. In this case, we still have to make O n squared distance computations, which does not improve the original time complexity. Luckily, we can apply the same intuition and further confine the search space along the y-axis. For example, if one point is at the top and another is at the bottom, they are obviously too far away, and we do not need to consider this pair. Specifically, for an arbitrary point P, we can define a horizontal band with a radius delta min around the line y equals to yp, where yp is the y-coordinate of the point P. You can also easily verify that the distance between P and any point outside of the horizontal band must be larger than delta min. In this case, we only need to compute the distance between P and the points within the horizontal band. By combining both constraints, we identify a square subspace, indicated by the purple bounding box, as the search space for points that could possibly lead to a shorter distance than delta min. Now, let's investigate how many points could be in the search space. Let's zoom into the search space and grid it into 16 smaller squares, each with a side length of delta min over 2. Note that the divider line is in the middle of the search space and does not go through any of the smaller squares. As a result, each smaller square must entirely belong to either of the subspace Q or R and cannot be in both. We claim that only one point can fit in a smaller square. This is because the farthest distance between 2 points within the same smaller square is square root 2 times delta min divided by 2, which occurs when the 2 points locate at opposite corners of the square. However, since both points are in the same smaller square, they are also in the same subspace, and their distance must be larger than the minimum within space distance, delta min over 2. As a result, fitting 2 points in the same smaller square will lead to a contradiction. Hence, each smaller square can fit at most 1 point. Given this fact, we can easily see that the search space can contain at most 16 points. Among those points, one is P, and the other 15 points can potentially form a between space distance shorter than delta min with P. Since P is an arbitrary point, we can extend this observation to all points. This means that for each point, we only need to compute a constant number of between space distances. Therefore, we should be able to compute the between space distance for the entire space in linear time. Well, which 15 points should we consider? Conventionally, we will consider P's next 15 points, ordered by their y-coordinates. Note that we don't need to consider the previous points because the distance calculation is symmetric, and the distance with the previous points should have already been considered. For example, the green point Q is before P, and it could lead to a better solution. The distance between P and Q should have already been calculated when we consider the search space defined by Q, which is represented by the dotted purple box shown in the figure. Therefore, when we consider the search space defined by P, represented by the purple solid box, we do not need to consider Q again. Now, we have discussed the general idea of the algorithm. Let's continue to outline the details. We can summarize the algorithm into 4 steps. First, we need to partition the input into 2 subsets, Q and R, such that each of them contains half of the input points. Second, we need to calculate the within space minimums, delta Q and delta R, using recursions, and determine delta min as the smaller one of them. Third, we need to calculate the between space minimum, delta QR, in linear time, using the banding technique discussed above. Finally, we need to compute delta QR and delta min and return the smaller one as the final result. Steps 2 and 4 should be straightforward, so we will focus on presenting details for steps 1 and 3. As you may have noticed, the algorithm heavily depends on the bands. To determine which points are within the bands, we need to consider their x-coordinates and y-coordinates. In this case, we will assume that we have the points sorted by their x-coordinates and also sorted by their y-coordinates. Note that we will not perform the sorting in each recursion, but just once before the recursion. As a result, the algorithm will still be able to run in O(n log n) time overall. It doesn't matter if you don't see it at this point, as it will become more apparent when we present the pseudocode. Let's now define some more notations. Denote P as the complete set of input points, Q as the points in the subspace Q, and R as the points in the subspace R. Further denote Px, Qx, and Rx as those set of points sorted by their x-coordinates. Similarly, denote Py, Qy, and Ry as those sorted by their y-coordinates. Let's look at the first step. Partition the points into two equal-sized subsets, Q and R. The main idea is to identify the median x-coordinate. Since we have Px, the set of points sorted by their x-coordinates, we can simply take the point in the middle and use its x-coordinate to divide the space. The corresponding function should take Px and Py as input and return Qx, Qy, Rx, and Ry. This is the pseudocode for the function partition points that performs the first step. In line 2, we identify x0 for the divider line. Then, in lines 4 to 6, we compare the x-coordinates of each point in Px with x0 and partition them into Qx and Rx. Note that this step does not alter the relative orders of the points in Px. Therefore, points in Qx and Rx remain sorted by their x-coordinates. Similarly, lines 7 to 9 compare the x-coordinates of each point in Py with x0 and partition them into Qy and Ry. Note that this function only checks the points in Px and Py once, and therefore runs in linear time. The third step is to identify the closest between-space pair, delta QR, in linear time. The main idea is, for each point, compute the distances with the 15 points in the confined search space and identify the minimum. The corresponding function should take Px, Py, and delta mean as input, and output the minimum between space distance, delta QR. Here is the pseudocode for the function closest pair between space. In lines 4 to 6, we check each point in Py to see if they are within the range x0 minus delta mean to x0 plus delta mean. If so, the point is added to the set By, which stores points within the vertical band. Note that because we start the process with Py, which stores points sorted by their y-coordinates, points in By are also sorted by their y-coordinates. Then, in lines 7 to 11, we compare each point in By with its next 15 points. Although there are two layers of for loops in the pseudocode, the second layer in line 8 only iterates a constant number of times. Therefore, the entire procedure remains in linear time. Then, we can combine the four steps into the recursive function shown here. The function closest pair of points recursive takes Px and Py as input and returns the closest pair of points in the whole space. In line 2, we perform the first step and divide the inputs into two subsets. In lines 3 to 5, we determine the minimum within space distance using recursive calls. In line 6, we compute the minimum between space distance. Finally, in line 7, we return the smallest amount of within space and between space distances. Note that all steps except the recursive calls can run in linear time. Based on our analysis of merge sort, we know that when we divide the input into two equal-sized subsets and complete all other steps in linear time, the resulting recursive algorithm runs in O(n log n) time. Hence, this function also runs in O(n log n) time. Finally, we present the wrapper function that includes the construction of Px and Py. We only sort the points by their x-coordinates and y-coordinates once before the recursion call. Overall, the entire algorithm still runs in O(n log n) time. In summary, we have discussed the 2D closest pair of points problem in this video. We have presented a divide and conquer solution that runs in O n log n time. Note that you can extend the same idea to higher dimension cases. For example, in 3D space, the bands will become rectangular prisms, and the confined search space will become a cube. It should be apparent that only a constant number of points can fit into the cube. We will not discuss the details here, but you can find more information online. Thank you for watching, and see you next time.